In the past few years, artificial intelligence has evolved at a breakneck pace, not just in scale, but in how we think about intelligence itself. We're no longer just training models to recognize cats in photos or translate sentences. We're building systems that can reason, plan, and even simulate aspects of human cognition. At the heart of this transformation lies a quiet revolution: the rise of large language models, or LLMs, not as mere pattern-matching engines, but as foundational architectures for general intelligence. But what if I told you that the real breakthrough isn't just the size of these models? It's what happens when they start to simulate themselves. That's the frontier we're now approaching: self-referential reasoning, recursive thought, and the emergence of what some researchers are calling model self-awareness, not in the philosophical sense, but in a functional, computational one. Let's start from the beginning. A language model learns from vast corpora of text, books, articles, code, websites, and learns to predict the next word in a sequence. It does this by adjusting billions of internal weights, forming statistical representations of language, syntax, and even logic. But here's the key insight. As models grow larger, they begin to internalize more than just word patterns. They begin to capture structural relationships, causal chains, analogies, logical implications, not because they were explicitly taught, but because they were exposed to enough examples where those structures appear. This is where things get interesting. When you scale a model to hundreds of billions or even trillions of parameters, something unexpected happens. The model starts to simulate reasoning. It doesn't just answer questions, it can generate step-by-step chains of thought, like, let me think about this. This is what we call chain of thought prompting. And it's not magic. It's emergent behavior, a property that wasn't programmed, but arose from the sheer complexity of the system. But now, imagine taking that one step further. What if the model doesn't just generate a chain of thought, but begins to reflect on that chain? What if it can ask, is this reasoning sound? Could I have made a mistake? What assumptions am I making? This is the next layer, self-monitoring. And it's not just a hypothetical. Recent experiments with models like Gemini, GPT-4, and Llama 3 have shown that when given the right prompts, these models can generate metacognitive outputs, not just answers, but evaluations of their own reasoning. How does this work under the hood? Let's dive into the architecture. At the core of every LLM is the transformer, a neural network built on self-attention mechanisms. Each token in a sequence is processed through a series of layers, where it interacts with every other token via attention weights. These weights dynamically assign importance, not just to nearby words, but to the entire context. This allows the model to build a rich, contextual representation of meaning. But here's the twist. When you start feeding a model a prompt that says, think step by step, then evaluate your reasoning, the model doesn't just process the words, it activates internal pathways that simulate a kind of internal dialogue. It's as if the model is running two parallel processes, one for generating the solution and another for auditing it. And crucially, this auditing isn't just a post hoc check, it's integrated into the generation process. This is where the concept of recursive self-improvement comes in. Some researchers have demonstrated that by having a model generate a solution, then evaluate it using a smaller, specialized model, or even a version of itself, the overall accuracy can improve dramatically. This is known as self-consistency, or self-reflection via iterative refinement. The model doesn't just give one answer, it generates multiple paths, compares them, and selects the most coherent one. But we're not limited to simple self-evaluation. In more advanced setups, models are being trained to simulate their own internal state. This involves techniques like internal state tracking, where the model learns to predict its own confidence levels, detect contradictions, or even identify when it's hallucinating, generating plausible-sounding, but factually incorrect content. One powerful method for this is called self-consistency with confidence scoring. The model generates multiple answers, assigns a confidence score to each based on internal consistency, coherence, and alignment with known facts. Then it aggregates the most confident responses. This isn't just a trick, it's a form of probabilistic reasoning that mirrors how humans weigh evidence. Now here's where it gets truly mind-bending. What if the model could learn to improve its own reasoning over time, not just through training data, but through introspection? This is the essence of self-improving AI. Imagine a system that can take its own outputs, analyze them for flaws, and then adjust its internal strategies, not by being retrained on new data, but by modifying its own inference process. This isn't science fiction. Researchers at DeepMind and OpenAI have already demonstrated systems that can refine their own reasoning strategies using reinforcement learning from human feedback, or even from self-generated feedback. The model isn't just answering questions, it's becoming a meta-reasoner, capable of optimizing its own cognitive architecture. But this raises a critical question. How do we know the model is actually reasoning, rather than just mimicking the appearance of reasoning? This is the challenge of interpretability. We can't open the black box and see thought like we can in a human brain. But we can probe it by testing its responses under adversarial conditions, by asking it to explain its logic, or by analyzing the attention patterns across layers. And here's a fascinating finding. When models are prompted to explain their reasoning, the attention weights often highlight specific parts of the input or earlier reasoning steps, not just the final answer. This suggests that the model is not just retrieving a cached response, but actively constructing a justification. The attention mechanism, which was originally designed for language modeling, has become a window into the model's internal logic. So what does all this mean for the future? We're moving beyond models that simply generate text. We're entering an era of systems that can reason, reflect, and improve themselves. This isn't about creating artificial consciousness, not yet at least, but about building machines that can handle complex, uncertain, and ambiguous problems in ways that were once thought to be uniquely human. And the implications are profound. In science, models could simulate experiments, hypothesize, test, and refine theories. In medicine, they could generate differential diagnoses, evaluate treatment options, and even flag inconsistencies in their own reasoning. In software engineering, they could debug code not just by finding errors, but by understanding the underlying logic of the system. But with great power comes great responsibility. As these models become more self-aware in function, we must ask, how do we align them with human values? How do we ensure they don't become overconfident in their own reasoning? How do we detect when they're simulating confidence without real understanding? The answer lies in hybrid systems, combining model introspection with human oversight, formal verification, and robust testing. We're not trying to replace human judgment. We're trying to augment it with tools that can think deeply, question themselves, and help us reach better decisions. So the next time you ask an AI a complex question, remember, you're not just getting an answer. You're engaging with a system that's learning to think, not just about the world, but about how it thinks.